Welcome to Tech Unplugged. We are diving deep into eBPF today, Extended Berkeley Packet Filter. And this is something that's becoming so vital in the Linux and cloud world.
Think of it this way. Sometimes you wish you could, see what's happening inside of your computer's engine room, right? I mean, like the operating system itself.
Right.
Well, eBPF lets you do that with Linux. You can actually tweak things without being a kernel expert or even having to restart your machine.
Wow.
Yeah, it's like a superpower.
Right. It's like you said, the engine room, being able to actually get down in there and see what's going on.
Exactly.
Well, we've done a lot of research on this topic at eBPF, trying to bring all the core essentials to our listeners, how it operates and why people are so excited about it in areas like security, networking, and observability, keeping your systems running smoothly. So let's unpack this powerful technology. What exactly is eBPF?
Well, at its heart, eBPF is like this revolutionary technology that lives inside the Linux kernel. And it allows you to run these small sandbox programs in a very privileged context, like the core of your OS.
Okay.
And the really cool thing is that it extends what the kernel can do safely and efficiently without you having to modify the kernel source code or load kernel modules.
So you're not having to get down into the nuts and bolts of the kernel.
Exactly.
You're working at a higher level.
Right. And you might hear the original version, which was mainly for network filtering, called CBPF, classic BPF, just to distinguish it from this more capable eBPF.
So CBPF is like the older brother.
Yeah.
And eBPF is the more modern version.
Exactly. More evolved. And here's a fun fact.
Okay.
The official mascot is a bee.
A bee.
Named EB.
EB. Okay. I love that. So it's like adding new capabilities to the heart of the OS without actually having to rebuild it or reinstall it. It sounds so useful. But how does it actually work? How does it get these programs running safely inside the kernel?
So it's this clever process. eBPF programs, they are event-driven. It's like setting up these tiny listening posts inside the kernel or even applications.
Oh.
And they just kind of wait. And when specific events happen, that's when they spring to action.
Okay.
These are called hooks.
Hooks. Yeah.
So these hooks can be things like when a program asks the kernel to do something, like open a file, that's a system call. Or when a function in the kernel starts or ends, or even low-level kernel events called trace points.
Okay.
And of course, network events when packets come in.
Right.
Now, if you don't have a built-in listening post, you can actually create your own. These are called kernel probes or K probes if you're tracing things at the kernel level.
Right.
Or user probes or up probes if you're looking inside regular applications.
Got it. So it sets up these event listeners. What happens then when an event triggers an eBPF program?
So the programs, they're usually written in a restricted form of the C programming language. And they're compiled into a special low-level code called bytecode, often using tools you might have heard of, like LLVM Clang.
Okay.
And this bytecode is loaded into the kernel using a specific command, the BPF system call. Now, here's where safety comes in. Before the kernel lets any of this code run, it goes through an intense inspection, like quality control, by a component called the verifier.
Oh, okay. So this verifier, that's the safety net. It makes sure these programs don't cause any harm to the kernel.
Precisely, and make sure it doesn't do anything dangerous, like getting stuck in an endless loop or crashing the system.
Right.
Once a program passes this check, the bytecode is then converted, on the fly, into native instructions using JIT compilation, just-in-time compilation, meaning it can run incredibly fast, almost as if it was part of the kernel itself.
So it runs fast because it's already there in the kernel. It doesn't have to make a call out somewhere else.
Exactly. It becomes part of it.
That is very interesting.
Yeah.
So near native speed, right inside the kernel. But with the safety guarantee, that sounds like a winning combination. You mentioned bytecode and a virtual machine. Are those related?
Yes. They are. So these eBPF programs are compiled into this universal bytecode, and this bytecode is then executed by a tiny little virtual machine that lives inside the kernel.
Okay.
That's what provides that safe, sandboxed execution environment.
Got it.
Like a little container.
Right. And we know the verifier is the Strix safety inspector. But what about these maps? What are those all about?
Yes. Maps. They're essential. Think of them like shared notebooks.
Okay.
That allows eBPF programs in the kernel to share data with normal applications that are running in user space.
Okay.
And they can even exchange information with other eBPF programs.
Got it.
There are different types of these notebooks optimized for different purposes, like quick lookups using hash tables, ordered lists using arrays, and managing frequently used information using LRU caches.
Okay.
streaming data using ring buffers, among others. And these maps, they can be accessible system-wide or just for a specific CPU core, so
Yeah.
they can be shared.
Okay, so the eBPF program is doing its work in the kernel.
Right.
And if it needs to store or share information, it can use these maps.
Right.
Makes sense. What about hooks? We talked about those before, like the triggers. Is there more to them?
Yeah, so hooks are the trigger points, the specific spots in the kernel or even in applications where you can attach your eBPF program to be activated. Remember those events. Trace points, kprobes, uprobes, system calls, network events. These are all examples of where you can hook your code.
Okay, so hooks are where that eBPF magic begins.
Hmm.
You also mentioned helper calls before. It sounds like they aren't completely isolated within the kernel.
That's right. So for stability and safety, eBPF programs, they can't just call any function they want inside the kernel.
Right.
So they have access to this curated set of pre-approved kernel functions called helper calls.
Okay.
And these helpers, they provide this secure way for programs to interact with the kernel, access memory in a very controlled way, and do things like getting the current time, accessing the maps, or even manipulate network packets safely.
Right.
And the cool thing is, the list of helper calls is constantly growing as eBPF evolves.
Oh, wow. So it's like a restricted but growing toolkit
Exactly.
that eBPF programs can use. What about tail calls and function calls? Sounds like we're getting into the more complicated stuff of eBPF.
Yeah. So to build more sophisticated programs, there are ways to link them together.
Okay.
So function calls, the standard kind, let you define and reuse sections of code within a single eBPF program.
Okay.
Makes the code cleaner and more manageable.
Right.
Tail calls are a bit more specialized. Think of it like one program handing the baton directly to another inside the kernel
Okay.
without having to return to the start.
Got it. Like chaining eBPF programs together
Precisely.
within the kernel to handle more complex tasks.
Yes.
Very interesting. Now, XDP, the Express Data Path?
Yeah.
Sounds like speed.
You got it. XDP is all about speed. It's a high-performance pathway for processing network packets, and it lets these programs access data incredibly early, right at the network driver level.
Oh, wow.
Super fast processing, even before the kernel's main networking stuff kicks in.
So it's bypassing a lot of the normal steps.
Exactly, bypassing all of that for really high-speed networking tasks.
Okay. And BPF type format. It sounds like it's about making things easier to understand for developers.
Absolutely. BTF provides all this information about the data types used in the programs and in the kernel itself.
Okay.
So this rich type information makes it much easier for developers to write, debug, and analyze programs.
And finally, we have BPF trace.
Yes, BPF trace.
That sounds like it's a user-friendly way to use all this power without having to write the raw eBPF code.
Precisely. It's a high-level scripting language, specifically for eBPF, and it makes it super simple to collect data from the kernel and analyze it. So you don't have to write that raw eBPF code. You can use BPF trace and its intuitive syntax to create really powerful tools with just a few lines of code.
Wow, that's a lot of information.
Yeah.
But I think we now have a foundational understanding of what eBPF is and how it works.
Yes.
So let's get to the why. Why is this such a big deal? What are the advantages?
Oh, there are so many benefits. The first one is performance. eBPF programs, they're compiled on the fly into machine code and run directly in the kernel, so they're super fast and efficient for tasks like processing network packets and monitoring. And in networking, you can actually move things that traditionally happen in the kernel to user space, reducing overhead.
So faster performance, greater efficiency, always a good thing. What else?
Security is a huge benefit. Remember the sandboxed execution and the verifier?
Yeah.
Well, they're key here. They prevent eBPF programs from causing system crashes or doing any harm to the kernel. So it's much safer than traditional kernel modules, which have unrestricted access. And since you're not modifying the kernel's code directly, there's less of an attack surface.
Right. Safer than kernel modules. Doesn't require kernel modifications. That's a big plus.
Definitely. And then there's the flexibility and convenience. You can extend the kernel at runtime without recompiling or loading modules. So for developers, it's often much easier to create code using eBPF compared to building kernel modules.
Right. It's a much faster process.
Right.
And what about getting better visibility into our systems? How does eBPF help with that?
That's where observability comes in. eBPF gives you this really powerful framework to trace processes and get deep insights into what's going on. And it doesn't have to stop programs to do it.
Wow.
Real-time, event-driven data capture.
So real-time insights without a huge performance hit.
Exactly.
Definitely.
Awesome and valuable for troubleshooting. And finally, there's programmability and expressiveness. With eBPF, you can create feature-rich environments without adding a bunch of complexity. The code runs directly in the kernel, so you can even maintain state between events, which isn't easy with other tools. And it can perform a lot of the functions you'd see in higher-level languages.
So it's very capable.
Very much so.
So we've got performance, security, flexibility, observability, and programmability. That's a pretty impressive list of benefits.
It is.
Let's see it in action. Where is eBPF being used in the real world?
All over. But let's start with security.
Wow.
eBPF is used for real-time monitoring of system events.
Okay.
It allows for early detection of threats and fast response by watching network traffic, system calls, and it can even enforce security policies by blocking or changing events.
So it's a kernel-level security guard that reacts instantly.
Precisely. And it gives fine-grained control over system calls and network activities to help identify and fix security holes. In containerized environments like Kubernetes, eBPF is key for monitoring and enforcing security at a very granular level, using those group hooks to control processes, resources, and network activity within containers.
That sounds really important for securing today's infrastructure. What are some other ways eBPF is used in security?
Oh, well, it's used to build advanced intrusion detection and prevention systems.
Right.
Or IDSPS for short.
Yeah.
By watching system calls and kernel events, it can monitor file system activity and detect or block exploits. You can even create your own security policies using eBPF and attach them to the Linux security module.
Oh.
Or LSM hooks. And if something bad does happen, it can help with incident response and forensics.
Wow.
By collecting detailed system activity data without you having to recompile the kernel.
So eBPF helps prevent attacks and understand what happened afterward.
Exactly.
That's impressive.
It is. Now, moving on to networking. Remember we talked about high-performance packet processing before? Yes, I do. Well, in networking, eBPF is really awesome for things like firewalls, load balancers, and network monitoring tools. It can handle huge amounts of traffic with very little delay. It allows for very efficient packet filtering, routing, and modification.
Yeah.
You can even add logic to parse new network protocols and program forwarding rules, all without leaving the kernel's fast path.
So it's streamlining things, making them much more efficient.
It is. And in Kubernetes, eBPF is used to optimize network paths, sometimes even bypassing more complex routing. It also helps to implement granular network policies for pods and hosts. And it even allows for something called connect time load balancing, which can reduce the overhead from network address translation.
Right. Cutting down on complexity and overhead. That's crucial today.
Absolutely.
Let's talk about observability and monitoring. How does eBPF give us a better understanding of our systems?
Well, eBPF provides real-time insights into system metrics, things like CPU usage, memory allocation, disk I/O. But what's really cool is you can define your own custom metrics and events. You don't have to just use the predefined ones, and all without exporting huge chunks of data.
So it's more customizable, more granular.
It is, especially in places like Kubernetes, where eBPF can give you detailed visibility into network stats and resource usage for pods and containers. And tools are using it to do things like trace TCP connections in real time.
Wow.
With very low CPU usage.
Deeper insights with lower overhead.
Exactly.
That's a theme with eBPF, it seems.
It is.
And finally, tracing and profiling.
Ah, yes. This is where eBPF lets you really look under the hood. It allows you to attach to trace points and probes to see how things are running, both applications and the system itself. And this can help solve really tough performance problems that you might not be able to find otherwise. You can collect detailed stats without having to export large amounts of data, and you can even build your own custom tracing tools.
Very cool. So across all these areas, security, networking, observability, and tracing, eBPF is really delivering. But let's be realistic. What are some of the challenges?
Sure. eBPF has so many advantages, but there are challenges too. One of the biggest ones is the complexity of development and maintenance. Writing good eBPF code often needs a pretty solid understanding of kernel concepts.
Do you need some experience with this?
Yeah.
Yeah.
It's not something you just jump into. Another challenge is kernel compatibility. What you can do with eBPF depends on the version of the Linux kernel you're running.
Right.
This can cause compatibility issues if you have different kernel versions in use.
So keeping up to date with your kernel can be important.
Absolutely. And while eBPF is designed to be efficient, if you write bad code or it's too complex, it can still eat up system resources.
Right.
So in environments where resources are limited, you have to be careful with eBPF or it could slow things down.
It's like any powerful tool, you have to use it responsibly.
You do.
Are there any security risks with eBPF itself?
Well, eBPF can be used to improve security. But if you're not careful, it could also make things less secure.
Okay.
If an attacker can load their own eBPF programs, they could bypass your security or gain access to your system.
Right.
So you need to be very careful with permissions. And always check eBPF programs thoroughly before you load them.
So securing eBPF is important. What about debugging? Is that a problem?
Debugging eBPF programs is definitely harder than debugging normal applications. They run inside the kernel, so you can't use the usual debugging tools. It's getting better, but it's still a work in progress. And lastly, like any powerful tech, it can be misused. Attackers who gain kernel access could use eBPF to hide what they're doing.
Right. So it's a double-edged sword.
It can be.
So what are some best practices for using eBPF, especially for security?
Great question. First off, keep your eBPF programs small, focused, and modular. Each program should ideally do one thing and do it well. This makes things faster, easier to debug, and reduces the risk of errors.
Okay. Small and simple. Makes sense.
Yeah.
What else?
Always test your eBPF programs in a safe environment before you use them in production.
Right.
This can help you catch bugs and problems early on.
Yes. Testing is crucial.
It is. And make sure you are using the right versions of your eBPF tools and libraries, like BCC and libpf. You want to make sure they work with your kernel version.
Yep.
And once you've deployed your programs, monitor their performance, watch their CPU and memory usage. Tools like BPF Trace can help with that.
So monitoring helps to make sure everything is running smoothly.
Exactly. Also use eBPF with your existing security and monitoring tools, things like Prometheus and Grafana for visualization,
Okay.
or your CM and IDSIP systems. eBPF can give those tools a lot more information to work with.
So integrate, integrate, integrate. What else?
Consider using eBPF to enforce your security policies directly in the kernel.
Oh, wow.
For example, you can restrict certain system calls or control access to the file system. And when you're building more complex solutions, break them down into smaller eBPF programs that can communicate with each other using the maps. And finally, connect your eBPF security with the rest of your security setup,
Right.
like your SIEM, iChips, and forensic tools, to make your overall security as strong as possible.
That's some really good advice. Well, we've covered a lot today. eBPF is a powerful and exciting technology that's changing how we think about security, networking, and observability. It's fast, flexible, and gives us incredible insight into our systems.
It truly is, and the potential is just growing.
From preventing kernel attacks and optimizing network traffic to providing granular monitoring with low overhead, it's amazing to see what eBPF can do.
Yes, and its adoption is growing because it solves real-world problems.
We encourage you to explore eBPF further. Look into tools like Cilium, Falco, Sysdig, Inspector Gadget, and BPF Trace.
Yes.
See how they use eBPF in practice, and see if this tech might be useful in your own work.
Definitely do that.
Well, thank you for joining us today on Tech Unplugged.
It's been a pleasure.
Stay tuned for more deep dives into the technologies that are shaping our world.